This video will present a set of algorithms that enable a group of robots to self-organize into a specific number of teams, or teams of a specific size, without any global knowledge such as absolute position or total number of robots. These algorithms were implemented within the Proto spatial computing language. A spatial computer is a collection of devices distributed to fill space, where the difficulty of communicating between devices is strongly dependent on their geometric distance. Proto is a language that makes it easy to write complex programs for spatial computers, and MIT Proto is an implementation of that language currently maintained primarily at BBN Technologies. In this video, we will be demonstrating our algorithms within ProtoSim, a simulator included with MIT Proto. An ODE-based plugin is being utilized to provide rigid body physics simulation. Robots will be represented as a set of cubes. A colored circle above the cube indicates which team a robot is associated with. These robots have a limited communication and perception range. The gray circles around each robot represent this communication range. The green lines indicate communication links between robots within range of each other. Additionally, the robots have no knowledge of absolute or global position. The algorithms we present have robots forming teams by forming chains, each with an arbitrary chain ID. Every robot in the chain follows the robot ahead of it. The head of the chain wanders randomly until it encounters a chain with a lower chain ID. At that point, it will move towards the tail of the chain in anticipation of it potentially being recruited. The tail of the chain attempts to recruit the other robots to join the tail's chain. It does this by broadcasting to the potential recruit what its position will be within the chain, the team's ID, and the chain ID. By modifying the conditions in which a robot will allow itself to be recruited, various team-forming behaviors emerge. The first algorithm we present will result in teams of size n. Each robot receives the target team size, n, and will allow itself to be recruited if its new index will be less than or equal to n. A plugin to ProtoSim enables us to modify this and other target parameters on the fly. Here, we see the user increase team size and larger teams begin to form. Next, we present one of two algorithms that enable the formation of n different teams. In the first one, each robot will always allow itself to be recruited, resulting in a single long chain. Within that chain, each robot assigns itself a team ID based on the formula, the ceiling of n groups times my index over tail index. We see initializing each team using a single large chain as a trade-off, enabling precise equal team sizes at the cost of initial mobility. As the specified number of teams changes, robots will modify which team they are associated with. Our second n-team algorithm takes a probabilistic approach to team assignment. Each robot randomly assigns itself a team ID between 1 and n. As robots wander, they will allow themselves to be recruited by chains with the same team ID as well as a lower chain ID. While this approach enables free movement of teams from the start, it gives only an approximately equal team size. If the specified number of teams changes, each robot will randomly assign itself a new team and chain formation will begin again, as seen here. Each of these algorithms are resilient in a wide range of situations. Here we see the robots reacting to a change in communication range by adjusting their velocity and the amount of space between links in the chain. The larger communication range makes it easier for robots to find each other. As the communication range decreases, robot speeds decrease as well, and chains group closer together to prevent chains from being broken. This video demonstrates resiliency as robots are randomly added and removed from the simulation. Removing robots, as seen here, has potential to break formed chains. If a robot within the middle of a chain is removed, the chain will potentially partition into two pieces and then heal immediately. If the two partitions are separated such that there is no communication between each partition, as seen here when a user interrupts the simulation and drags a section of a chain across the arena, the tail recognizes it's been disconnected and attempts to create its own chain. Adding robots is no different than discovering new ones. The only limit on the number of robots being added is due to the size of the arena and it becoming overcrowded. Here we see an increase in arena size supporting significantly more robots. Due to our algorithm's reliance on vector math, we are not limited by the number of dimensions. By modifying the parameters of our physics simulation, we are able to demonstrate that these algorithms will also work in three-dimensional settings.